statement that said, when the grade is small, you can do it the right or wrong way, no problem, and there's not much of a difference. Which begs the question then, what question does that beg?
What constitutes a small grade?
What constitutes a small grade? So what we can start doing is we can start figuring out boundaries for what constitutes a small grade, right? For example, we know the quiz grade was pretty small because they were almost exactly the same grade. So an angle of 2 degrees is pretty small. A grade of, what, 2%, I think you guys said it was, 2%, whatever. So let's go back to that after we attack this. Green. Who's feeling brave? Let's do this together, yes? Let's make sure we're happily solving this, yes? Help me out, help me out, help me out. Jessica, do it!
Oh, I have to do it?
Well, not only did you raise one hand, you raised 2 hands. You got this, girl. Go.
Oh, just tell you?
Just walk me through it. Yeah, walk me through it. Yes, ma'am.
Okay. So I did 6 squared plus r squared
Cool.
equals 10 squared.
Good. So you see, stop right there, Jessica, if you don't mind. That's beautiful. You see, it's the same equation, but the unknown is in a different place. And that does make a difference in how you solve it, right? That does make a difference in how you solve it. Because on this one, everything was on one side. We simply crunched everything down, exponentiated, then added, and then took a square root. It's going to be similar in this one, but we've got to do some moving around first, don't we? So Jessica, what'd you do next?
Then I squared the numbers that I knew.
So you get 36 plus that run squared. That's 100, right? Beautiful.
I subtracted 36
from 10. This is a little bit different. We had to add the previous one. We had to subtract in this one. You got to undo that addition. So you get the run squared is, what's that, 64?
Yep. Square root of both. Yep.
Root of both sides? Run is?
8.
8. I'm trying to use nice numbers in these because I don't want to focus on the annoyance of the arithmetic. I want to focus on the niceness of the formula.
I did it actually like the square root of 10 squared minus 6 squared equals 8. It works.
You've got a 4-letter name.
Jordy.
Jordy. There it is. That's all I can remember though. There's 4 letters in that name. I was pretty sure it ended in an I. Okay, so what Jordy did was, she actually did all the math in one step. There's absolutely nothing wrong with doing that, so long as you obey order of operations, and I'll tell you what I'm talking about here in a moment. Are we cool with the 8 first?
Yes.
So I got no argument with this whatsoever. That would be an 8. It's one of those special triangles called 6, 8, 10, 3, 4, 5. There are special whole numbered ones in geometry. I'm trying to make those up in my head as we go to make the arithmetic happen nicely. What Jury said, and I think this is a great idea, is she basically went straight from this step to this step. And you can do this. It depends on how comfortable you are with the algebra. You can do all of these arithmetic steps in one move. You could subtract the 6 squared from the 10 squared and then take the square root of the result. So you can go straight to this. Run equals the square root of 10 squared minus 6 squared. Jury, the only reason I don't go back to that is, number 1, some students don't like it. It's cool that you do. Number 2, very often students will then make a mistake at this point. And you know what it's one of my top 5 math mistakes students often make. What's the mistake?
You square root before you...
Exactly. They take the square root of 10 and the square root of 6 and subtract them. And they call the answer the square root of 4, and they call it 2. Which, I mean, if you do that quickly, you're like, oh, that makes perfect sense, except it doesn't. Because if you then look at the triangle, that means this piece here has to be 2. There's no way for that to be 6 and this to be 2 and that to be 10. That can't happen, because in a triangle, any 2 sides have to be bigger than this 3rd side when you add them together, otherwise they can't connect. Think about it this way. It's easy to draw, it's easy to say, yes, but I call that 2 and boom. Well, you can call it that, but think about it from the length of, say, 10 inches. If the long side were 10 and one side were 6, that would stretch to just about there, right? 6. And then 2 would be just about like that. They don't touch, which means you can't raise them and make them touch either. The 3rd side has to be less than the other 2 sides combined in order to actually be a triangle. It's called the triangle inequality. It's one of the really cool results from geometry. So I know it can't be 2. It just can't be, because it wouldn't make a triangle at that point. But it's so easy mathematically. Just go square root of this, square root of this, blah, blah, blah. So here's the best hint I can give anybody who likes Jury's way, which I think is badass. but who's afraid of making that mistake, here's something you should always put if you're uncomfortable with square root symbols. When you take a square root of anything, put what you're taking a square root in parentheses. Put it in parentheses under it. Because you know in order of operations, parentheses mean do everything that way first. If you put parentheses around the square root, which if you've noticed, if you press the square root button on your calculator, what comes up? Parentheses. One of my favorite things TI did when they went from the 82 to the 83. I wish they'd do it when you hit a division sign. I wish they'd do it when they hit a multiplication sign. I wish they'd do it in almost every function. In almost every function they do. The tangent function, if you press that tan button, left parentheses come up. If you press the sine, the log, the natural log, why not square root? Or why not fraction block? I don't know. Because I don't code them. Yes?
Are we gonna do logs and after logs?
No.
Okay.
No, I mean, I hinted them in 243 because they become a little more prevalent there, but I've discovered in 105 there are more, what's the word? More popular ways of getting at an answer than logs and natural logs.
Because we did it in 111.
You did.
A lot of.
It is. It's a big chunk of 111, and I call it like the huge hoop that you have to jump through in 111. And there are many, many ways to get around it. And we'll deal with that when we do exponential growth. Math 105, exactly. And we will do exponential growth like 111 did. But we're not going to attack it via logarithms. I don't want to scare anybody out by saying this word logarithms. Don't worry about it. Cool? Now at the risk of running, want to do one more? Would one more be, I mean, the third one I was going to do was to make the run and the hypotenuse known. But that's a little fictitious from a grade point of view, because you're never going to know those two things. You'll know the hypotenuse, but you're never going to know the run and the hypotenuse without knowing the rise. That doesn't make any sense, does it? I mean, you would definitely get the rise, because if you have an elevation tracker on your phone, you'll know where you started, and you'll know where you ended. So you've got the rise. And then if you're looking at either your phone or your car's odometer, you'll know how many miles it took you to get there. So at worst, you're going to have rise and hypotenuse. At best, you're going to have rise and run, but you're never not going to have the rise. So it seems kind of silly to do a third example. And the math would be the same as the second example anyway, wouldn't it? Fair? Yeah, hopefully you see that. So good. All right. So that's, as far as the review of that kind of math, that's all we got to talk about. That's the only thing I think that was giving some people some agita, was that kind of quadratic. Now we'll see quadratics again when we do the bike timing down that hill over there. Look at that hill over there. We're going to time my bike going down the hill and figure out how fast I'm going. We'll need quadratics then. But we're not going to solve them using factoring or the quadratic formula. We're going to either graph them or approximate them using other methods. This is how to get around logs too. So, yeah? You getting that look? Let's take 5, yes? Let's go wander around and take 5 and come back to this great question that Christy mentioned.